All right, so hello everyone, I'm Gali Noti and I'll present a joint work with my advisor Noam Nisan. And in this work we suggest a new method that we call the Quantal regret method that addresses the following challenge. So let's look at this picture here and assume that we are looking at some empirical data of human players who played some game repeatedly. And in the data we can observe the actions that the players played, for example, the sequence of bids that they made in repeated auctions, but we cannot observe their private parameters, such as their true values, by how much they really value this item for sale. Sorry. Now, when we approach such data, we need to have good estimates for such private parameters, and that's in order to make all sorts of analysis about the data. So the challenge is how can we reliably estimate the players' unknown parameters from their observed actions in repeated games? Just to make it more concrete, let's just immediately look at this very simple example. So assume we have a simple 2x2 game that is defined by this payoff matrix on the left. So first, how to read it. We have here two players, the row and the column players. In every game period, the row player chooses to play either up or down, and the column player chooses left or right. And for example, this outcome here, where the row player plays up and the column player plays right, gives a payoff of 0 to the row player and 18 to the column player. And as you can see, 2 of the 8 payoffs, parameters that define this game are hidden here by x and y. And we also know that when human players play this game repeatedly for some specific values of x and y, these were the empirical frequencies that each of the 4 possible outcomes was observed. Now we want to use these observed data to infer, to estimate what were the true values of x and y that were used in the experiment. So let's take the parameter x, for example, and try to think what should be your prediction of this missing parameter x when you know that these results were observed with human players. And the standard approach is to assume that the players reach a Nash equilibrium of the game, and then we can just calculate this Nash in terms of the missing parameter, and in this example that will be pretty simple since there is only a single mixed Nash equilibrium where the column player must play left with a probability of 10 over x plus 1. And then we can just extract an estimate for x by substituting the empirical frequency. We observed that the column player actually played left, and then we get in this example 13.7 here. But in general, assuming equilibrium can be problematic for many reasons because, for example, we know that if the players are, there can be multiple equilibria, so it is not clear which one of them we should take as a prediction or how exactly players should coordinate on a specific one. But a point that is maybe more important for the discussion here today is that it is not clear if we can really expect that human players will reach this mathematically defined Nash equilibrium. And a second, much more robust approach was suggested here in EC 2 years ago by Nikipelos, Silkanis, and Tardos. And they also got the best paper for that. And they suggested to perform this estimation based on a weaker assumption that the players minimize their regret in the repeated game. And the regret here is in the usual sense for the regret minimization literature that defines the regret for a player by the difference between the optimal utility the player could get by playing the best strategy through all the games and his actual utility in the games. And the method that relies on this assumption will calculate for each possible value that the missing parameter x can have, what would be the regret for the player had this been the true value of the parameter. And in this example, if we compute the regret for the row player for all integers from 0 to 30, this is the regret curve that we get. And the method selects the value that minimizes this regret curve as the estimate for the missing parameter. In this example, the regret curve is minimized for x equals 13. Now, this approach has significant advantages. First, it is a strictly weaker assumption than assuming Nash, because we know that if the players are in a Nash equilibrium, they're also minimizing their regrets. But if we assume regret minimization, it allows for much wider families of equilibria, and there are also many natural learning dynamics that guarantee low regret. And the second important point is that notice that this method is general. It was suggested from the context of ad auctions, but it is in fact general for most repeated game settings. And in the previous paper, we compared this mean regret method with methods that rely on the equilibrium assumption. And that was in the context of ad auctions. We used data from a previous experiment that we ran with human players. And we found that indeed the mean regret was at least as good as the equilibrium-based methods in estimating the private values of the players in our experiment. But on the other hand, we also saw that the improvement using the mean regret was only minor, and both methods still had quite high errors. So now we suggest what we call the Quantal regret method. And here, instead of assuming that the players optimize perfectly, it only assumes that they are more likely to act in a way that gives them lower regret. And what the method does, roughly, it also looks at the regret curve, but now instead of taking the minimal point as the prediction for the value, it takes a weighted average of the possible values for the parameters with weights that are decreasing with the regret. And specifically, we take these exponentially decreasing weights. And in the exponent, we have lambda that we call the regret aversion parameter. And as you can see, for large values of lambda, the Quantal regret estimate approaches the mean regret estimate. So you can think about our method as a generalization of the mean regret method. In this example, for lambda equals 3, the estimate will be 10.2. I'll show later how we suggest to determine the value for lambda, and we will see that in fact, the improvement using this method is very robust to the choice of lambda, but more about that later in the slides. Now, just to wrap up this example, so we got 3 different estimates using each of the 3 different methods for this missing parameter x. And in this example, the correct answer was 10. 10 was the value that was actually used in this experiment and gave these results with human players. You can see the Quantal regret was significantly closer to the correct answer, to reality, than the other 2 methods. But we will see that it is not just this specific example, but in fact, for the 2 different data sets that we tested, we had the same conclusion that the Quantal regret was significantly more precise than the mean regret, which was in turn slightly more precise than the equilibrium-based methods. All right. Now, before we move on to the experimental evaluation, just a bit more details about the Quantal regret method. So this is the setting. We're talking about n players who repeatedly play a game. We denote by theta I the unknown parameter for player I, which we do not observe in the data, and this is what we want to estimate. We do observe the sequence of actions played by all players in T repetitions of the game, their utility functions that actually define the game. The utility for every player depends on the actions made by all players, as well as on his own private parameter theta I. And we also have some prior distribution on possible values of theta I. We will just use the uniform prior in our results. And the goal is to estimate theta I based on these observed data. And what the method does, so it goes over all possible values of theta I in principle. If it's too much, we just take some reasonable grid of values. And then it calculates for each value the regret for the player had this been the true value of the missing parameter, theta I, for the actual sequence of actions that was actually played. And then the estimate is this weighted average of possible values of theta I according to the prior with exponentially decreasing weights in the regret. And the idea behind choosing this estimator is the behavioral assumption that we make that the probability that the player played any particular sequence of actions is exponentially decreasing with his regret. And this estimator is the one that minimizes the mean squared error for this assumption. And as I said, we have lambda in the exponent, which we call the regret aversion parameter. And you can see that lambda has to be in the same scale or related to the scale of the regrets in the game that we are considering. And we suggested to set lambda to be the inverse of what we believe as the minimal gap in utilities that human players would consider significant in the specific game that we are considering. And in the results that I'll show, we took lambda to be around 3% of the typical value in the game, but we will also see that as long as lambda is in the correct scale, the results are robust to the choice of lambda. So we evaluated the Quantal regret method on 2 different data sets from experiments with human players. Now, we took controlled experiments where people sit in a laboratory and we know all the parameters. And so what we could do, what we did basically, we looked at the data. We then hid from ourselves a basic parameter x in the data. We then tried to estimate x from the observed data using each of the methods. And then we unhid and compared the estimate that we got with the true value that was actually used in the experiment. And the first data set is from the 2x2 games from the experiment of Zelter and Mura from 2008 that we already used for the first example. And here in each experiment session, they had human subjects who played a 2x2 game for 200 periods. The data was like in the example, the empirical frequency of play of each of the 4 possible outcomes, like in this matrix on the right, and also the payoff matrix that defined the game. And they had 12 different games. All of them had only a single mixed Nash equilibrium, non-negative utilities. And the estimation task that we defined here was, for each session, we estimated separately each of the 8 payoffs that defined the game, like we did for the parameter x in the example. And we found that the quantum regret significantly outperformed the mean regret, which was in turn slightly better than the equilibrium-based methods, according to the 3 measures that we tested: the root mean squared error, this is our main measure, RMSE, average error, and also the hit rate, which is the probability that we were correct, that we were within a delta of 3 from the true value of the parameter. And this table summarizes the results over all sessions in the experiment, and you can see that the quantum regret had much lower error and higher hit rates. And the second data set is from the ad auction experiment that we ran. And here in each experiment session, we had 5 human players who simulated the roles of the advertisers and competed in a stream of 1,500 auctions for 5 ad positions in decreasing click-through rates. And in the beginning of every session here, we assigned each one of our 5 players a value per click, which was his private information. And this is what we used to determine his payoffs in all the coming auctions. And the estimation task was to estimate, to recover this private value for every player from the bids that all players made in the repeated auctions. And we had here 4 experimental settings. We compared the GSP, generalized second prize auction, that is usually used in this setting, and the VCG auction rule, and also 2 information settings. And again, we see that the quantum regret was significantly better than the mean regret by a large gap, and then the mean regret was slightly better than the equilibrium-based method. And here, these columns show overall VCG sessions, and these columns summarize overall GSP sessions. Now, the true regret-based methods are general, work just the same like I presented. The equilibrium-based methods are specific to the context that we're considering. In VCG, it is simple since it is a truthful mechanism, so we just take the average bid that the bidder played as the estimate for his value in the auctions. The GSP is more complicated because there is no dominant strategy, and there could be many equilibria, so we just compared with the 2 methods that were suggested in the literature for this task in the GSP, Varian from 2007 and Ethy and Ekipero from 2010. And you can see that in all cases, the quantum regret had a large advantage, error much lower, and the hit rates are higher. All right. And in the paper, we show that these results that I just showed you, their summary, are in fact very robust to the specific details of the experiment and to different implementation variants. And here we see that they were robust to the choice of lambda, the regret aversion parameter. And this graph, each one of the graphs show the RMSE, the error, as a function of the lambda values. This is for the 2x2 game data set, VCG auctions, and GSP auctions. So you can see that the error using the quantum regret, which is the blue line, is lower than the error using the other methods for a wide range of lambda values. The green line shows the error using the mean regret, and then the red lines are the errors using the equilibrium-based methods, and these are the highest in all 3 cases. Now, for lambda values that are near 0, the error using the quantum regret is again large, since what the method does in these cases is just ignores the regrets and averages according to the pile. All right, and just to conclude, so I presented the Quantal regret method, and we saw that it gave, with human players, significantly better results, more precise than the mean regret or the equilibrium-based methods, and that was for the 2 data sets that we tested. It's interesting to see if it will work just the same for other repeated game settings, and also to test implications of using this method to real auction data. And that's it, thank you.